Hello everyone, my name is Rohan Banerjee. I am from TCS Research, Tata Consultancy Services, Kolkata, India, and in this video I am going to present my paper Noise Cleaning of ECG on Edge Device using Convolutional Sparse Contractive Autoencoder. This slide covers a brief outline of my presentation. I'll start with an introduction, problem statement, then I'll quickly talk about the basic theory of denoising autoencoder. Next comes our proposed architecture, then I'll talk about the techniques to optimize the baseline model to effectively run on low power edge devices. Then comes our experimental results followed by a conclusion. Electrocardiogram or ECG measures the electrical activities of the heart. It is widely carried out as a routine test for first level diagnosis of any cardiac problems. However, manual inspection of any disease from a 24/7 ECG recordings is often difficult, which requires the help of digital techniques. Automatic diagnosis from the ECG is possible thanks to the recent advances in AI and ML based techniques. However, ECG signals are prone to background noise due to motion artifacts during recording, improper sensor placement on the subject body, and also the induction effect of nearby devices. Hence, denoising of ECG is considered as a prerequisite for automatic ECG diagnosis. Noise cleaning of ECG signals has been a popular area of research. The existing approaches can either be of signal processing or deep learning based. Bandpass filter is the simplest form of ECG noise cleaning. However, it cannot remove the in-band noise components. Adaptive filter, empirical mode decomposition, or principal component analysis have been successfully deployed. Whereas the deep learning based approaches typically generate a denoising autoencoder. Although the deep learning models often outperform the signal processing based approaches, however, they generate large model which has issues in real-time deployment, and also deep learning models are often prone to an overfit. Our main contributions in this paper can be summarized as follows. We propose a sparse contractive convolutional denoising autoencoder for noise cleaning of ECG. The deep learning model is duly optimized to run on low power edge device for real-time ECG cleaning. The denoising performance of the method is qualitatively evaluated on a public dataset in terms of detection of abnormal heart rhythms using available machine learning classifier. We do a detailed comparison of our approach with a number of existing ECG noise cleaning algorithms. Finally, the optimized model is deployed using commercially available components for real-time ECG noise cleaning. A denoising autoencoder is specially designed for noise cleaning of image or time series data. Here the input is first corrupted by addition of noise and the noisy input is fed to the encoder. The encoder maps it into a lower dimensional latent vector, whereas the decoder tries to reconstruct the actual non-noisy data from the latent vector. During training, the mean squared error between the original and the reconstructed non-noisy data is minimized using backpropagation to learn the network weights. Like any other deep learning models, an autoencoder is prone to overfit. We apply a number of regularization terms to the network loss function in order to overcome the situation. Initially, a sparsity penalty term is added to limit the overall activation of the encoder neurons. Here, average activation of a neuron is forced to be close to a predefined value by minimizing their KL divergence. This term is added to the network loss function. This approach helps the model to respond to the unique statistical properties of the training data. Secondly, a contractive regularization term is added so that the model is less sensitive to minor fluctuation of the training data. This term is basically the Frobian norm of the Jacobian matrix of the encoder activation with respect to the input. Finally, the neurons of the encoder and the decoders are regularized via L2 norms. The cumulative loss function contains the sum of all three regularization terms. Architecture of our proposed 1D convolutional denoising autoencoder is shown in this figure. Tensor dimension at the output of each layer is duly mentioned. Noisy ECG signals are first broken into non-overlapping rectangular windows of 1024 samples. Each window is considered as independent input to the autoencoder. The encoder contains a total of 3 convolutional layers. The kernel size is selected as 5 for performing the convolutional operation, and 20 filters are used in each layer. Zero padding is applied to the input in each convolutional layer for retaining the original dimension of the input. Rectified linear unit function is used for nonlinear activations of the neurons. Dimensions of the output feature map in each convolutional layer is reduced by the associated 1D max pool layer having a pool size of 2. The feature map at the end of the third max pool layer is flattened and applied to a dense layer to convert the encoded latent vector of length 512. The decoder follows an inverse structure to the encoder. However, the max pool layers are replaced by upsample layers to gradually increase the dimension of the output feature map. There is an additional convolutional layer in the decoder having a single filter with kernel size of 5 followed by a sigmoid activation function to convert the reconstructed data to the original 1D data space of the input. Sparsity and contractive regularizations are added only to the convolutional and dense layer of the encoder, whereas L2 norm is applied to all but the final convolutional layers of the decoder. The baseline model of the proposed autoencoder is trained on a desktop. A standard deep learning model trained on a desktop or a server needs significant optimization in order to efficiently run on a low power edge device. In our application, we select Raspberry Pi 3 model B+ as the target edge device to run the denoising application. The following steps of optimizations are applied to compress the baseline model. Depthwise separable convolution. The standard convolution operations in the baseline model are replaced by depthwise separable convolution. In this process, each convolution layer first performs a depthwise convolutional task that acts separately on the channels, followed by a pointwise convolution operation that mixes the channel. This process not only reduces the model size due to fewer parameters but also results in a faster inference speed on target device due to fewer mathematical operations. Weight pruning. The model size can significantly be reduced by eliminating lesser important connections by replacing them with zeros. A significant number of connections in a neural network model is found close to zero. Weight pruning is a technique to gradually zero out few such insignificant weights during training in order to achieve model sparsity. Such pruned models are easy to compress, which reduces the model storage area without significant impact on model accuracy. Weight pruning requires a retraining of the baseline model by a gradually increasing sparsity in an iterative manner. The baseline model weights are taken as initial weights. We start by adding 30% of sparsity to the baseline model and finish at 50% of sparsity using a polynomial decay function, which causes a minimum performance drop in the pruned model. The part out model is retrained in the process to minimize the loss function. Post-training quantization. A model trained on a high-end computer system may not run effectively on a low-power edge device due to hardware constraints. In post-training quantization, the pruned model is further optimized by quantizing the 32-bit floating point weights of the trained model into 8-bit integers. This process not only reduces the model size but also improves CPU and hardware acceleration latency with a little impact on model performance. We apply dynamic range quantization on the pruned model, which statistically quantizes the weights. During inferencing, the weights are reconverted from 8 bits precision to floating points using floating point kernels. This conversion is done only once at the target device and cached to reduce the memory. Noise cleaning performance of the baseline autoencoder on sample ECG recordings are shown in the figures. Here, the sample recordings are obtained from a simulated ECG database and also from the PhysioNet Challenge 2017 database. The proposed autoencoder is compared with two signal processing approach, a bandpass filter based noise cleaning and a wavelength based noise cleaning. The figures clearly indicate that the proposed autoencoder outperforms the signal processing based approach as it is able to reconstruct all the important ECG components from noise contamination. The baseline autoencoder is evaluated on a simulated ECG dataset and also on the PhysioNet Challenge 2017 dataset. A detailed quantitative evaluation on the simulated dataset is shown in this figure. Here, the reconstruction loss is reported in terms of root mean square error RMSE between the original non-noisy and the cleaned waveforms. The original signals are corrupted by addition of noise in order to achieve SNR of 3 dB, 0 dB and minus 3 dB respectively. Apart from filter and wavelet based denoising, we also consider two other deep learning approaches for performance comparison. Owing to the rigorous regularization steps, the proposed autoencoder efficiently learns the statistical properties of the training data at different SNR levels and is less vulnerable to the minor fluctuation. Hence, it is found to yield the least RMSE in overall signal reconstruction compared to the prior approaches. This figure shows the performance evaluation on the PhysioNet Challenge 2017 dataset. We perform a qualitative evaluation of the baseline autoencoder in terms of usability of the reconstructed signals in a real-world application. The PhysioNet Challenge 2017 dataset, which contains around 8,500 single-lead ECG recordings labeled as normal AF and other abnormal rhythms, is selected for that purpose. An open-source machine learning algorithm for identifying different rhythms is selected. The algorithm first derives a set of 150 handcrafted features related to ECG morphology and short-term heart rate variability. The feature set is applied to a series of cascaded binary AdaBoost classifiers for classification. Classification performance is reported by the metric FT, which is basically the average of F1 score of detecting normal AF and other rhythms. Median value of the metric FT is measured as 0.85 on the original non-noisy dataset in a 5-fold cross-validation. Subsequently, the signals are contaminated by addition of noise. Then the signals are denoised using various denoising approaches, and the disease classification algorithms is evaluated. The table shows that impact of various denoising approaches on the noise cleaning performance. Although the existing approaches are effective at an SNR of 3 dB where the signals are less corrupted, their performance tends to drop with a reduced SNR. You can see that there is a significant performance drop in disease detection rate at SNR of -3 dB, whereas our proposed approach is more reliable to reconstruct the signal morphology at all noise levels. The disease-specific features are thus less erroneous, resulting in a commanding classification performance even at an SNR of -3 dB. A prototype end-to-end system is designed for real-time ECG denoising using commercially available low-power, low-cost components. AD8232 is a fully integrated portable single-lead ECG front-end. It has an operating voltage of 3.3 volt and it comes with 3.5 mm jack for connecting the electrodes to human body for measuring of ECG as analog voltage. The analog outputs is applied to a commercially available multi-channel 10-bit analog to digital converter. The ADC communicates with the GPIO pins of the Raspberry Pi device via serial peripheral interface for synchronous data transfer. The optimized model is copied to the Pi for inferencing. The users are asked to perform random body movements to introduce real motion artifacts in the ECG recordings. The noisy ECG streams are digitalized and accumulated at the Pi at a sampling rate of 100 Hz, and denoising is performed on every 1024 samples. 2 buffers are used in the application to speed up the processing. Data in one buffer is being processed while the next stream of data is read into the other buffer in real time. The figure shows a noisy ECG stream as recorded in the Pi and the corresponding noise cleaning performance. Depending upon the number of heartbeats, the denoising time for a 1024 ECG samples is measured as around 41 milliseconds. This table shows the mean root mean square error in reconstruction of ECG on the target edge device after optimizing the baseline model at various SNR levels. It can be seen that there is no significant impact on the autoencoder performance after optimization in overall root mean square error compared to the baseline autoencoder. However, the optimized model is almost 10 times smaller compared to the baseline model, and it can be easily fitted to run on a low power edge device. It's time for conclusion. ECG signals are vulnerable to background noise. Effective noise cleaning is a prerequisite for automatic AI diagnosis from digital ECG data. In spite of numerous works, effective ECG denoising still remains an open area of research. In this paper, a convolutional sparse contractive autoencoder structure is proposed. The autoencoder is found to outperform a number of existing approaches. We also duly optimize the baseline autoencoder to effectively run on low power edge device for real-time ECG denoising, and a prototype system for the same has been designed. However, the model is still unreliable for very noisy ECG signals where the SNR is lesser than -3 dB. Introduction of generative model for potential morphological reconstructions can add value to the existing model for an improved noise cleaning algorithm. Thanks for your patience, and I am available to answer your questions if you have any.